just one thing related to analyticity, holomorphicity. Let me make sure I'm recording. I am recording. First off, a happy birthday to Miss Sydney, right? We got this? Like, yeah, happy birthday. Drink lots of fluids and like electrolytes so you can recover fully.
So they should recover.
Is this your 21st birthday?
It's
22nd, I
22nd.
think.
Oh, okay.
Yeah. So yeah, she knows.
Yeah,
that.
she'll be fine. She's a pro now. Yeah. Good. First off, let me see, do you have any questions on the homework? Does anyone besides Lavina have questions on the homework? No, I know you have some. I'm just checking. I can count on you to have some. Noah might have a few. And it's also, I think it's Olivia's birthday. We missed Olivia. So Olivia's happy birthday. She's not here because she's celebrating her birthday.
Wait, it's her birthday today?
What's, I think it's either today or yesterday.
Wait, so
Grace's
that
birthday
is-
was yesterday.
How old are you?
20.
20. Oh, wow.
No, I tend to be a little young for my grade.
That's good. That's good. Much life left. Yeah, I don't think I did the like, I'm gonna go out and poison myself with alcohol thing, like when I turned 21. But I had a lot of other things going on at that time. So, yeah. We need to chat about that.
How do you show that for 2.6, for all straight lines, should we just input y equals mx or something?
Yeah, let's talk. That's a great question. So in 2.6, we've got function in rectangular-ish form. Well, no, this isn't even a complex function. Oh, it is. It's just a real valued complex function. So that's interesting. So notice that f maps from C, but its outputs are strictly real. There's no I there. We're grabbing the real and imaginary parts, combining them into a real number. There's certainly some numbers that x and y shouldn't be, like it shouldn't be 0, 0, and I think they say that, so this is C minus the origin, which makes sense. So show that the limits of f at 0 along straight lines exist and are equal. So to do this, what we're going to do is we're going to just set up an arbitrary line. And you can do this by saying, I've got a complex number where y equals a x, and a is just a real number. So your complex numbers all along this line are z equals x plus ax, where this a is a fixed number. And this handles everything except vertical lines. So to approach on we would want to address this just for completion, and this is actually pretty easy. To approach on the imaginary axis, I would just use z equals iy, and then just let y go to 0. So, in other words, here the x's are all 0, and look, what happens when x is 0 and y is not 0? What is f of z at that point?
When x is 0, y is
One
not
over
0.
y
Yeah.
squared? No, just one.
Um,
Or 0.
Yes, just 0. Yeah, right, when x is 0 and y, it's important that y is not 0, and it can't be because we've actually taken it out of the domain. But when x is 0, we got 0 over non-0. So right here, f is identically 0 there. So we should expect, hopefully, these limits along these lines will also be 0, because if they're not, then this problem is setting us up for failure. It's a lie. So to do this limit, you could combine these two things, and you could say that the limit as z goes to 0 of f of z is actually also equal to the limit as, whoa, weird, pretty weird, okay? I do want to use that at some point, but no, I don't know where. I have no idea what state it's in. It's the limit as x plus iy goes to 0 of f of z, which is the limit along any way this approaches 0. So it's also the limit along x plus I ax going to 0 of f of z. And let me write one more thing. This is the limit as x goes to 0 of f of x plus iax. I'm kind of like just slowly creeping up on it, being a little bit careful, like kind of each step of the way thinking. These all say the same thing, except up to here where we say approach along a specific path and it needs to be the same answer as that limit. And then here I'm just kind of flipping things around. So in other words, this is limit as x goes to 0 of, and I'll get you started here, x squared, and here y, this is y, right? So that's ax squared over x to the 4th plus ax squared. And again, a is a real number. Luke.
In the original problem, the top y wasn't squared.
Oh, it wasn't. Oh, really?
I don't know if that
Yeah,
changes anything. Other than
I
that
don't know why I
last
read
little
that. Yeah,
bit.
you're absolutely right. It will change some things, definitely. It won't change any of this, luckily. It won't change anything up until here. So thank you for catching that. That's really important. Let's do a little simplification and just look at this because I feel like it's been a while since you've done a limit like this. So we get x to the 4th is a squared x squared. First step, so you see a limit, it's a quotient, immediately you're like, and especially with approaching 0, you gotta be worried about 0 over 0. So first step is plug in the limit point, see if you don't have 0 over 0. If you don't, you're good to go. Well, you don't want to divide by 0 either. But if this turns out to be some number after I do the plugging, I'm good to go. That is not the case here because I've got a 0, I've got an indeterminate form. How do we handle indeterminate forms of the 0 over 0 ilk? Baha?
Yeah, I think so.
What'd you say though?
Like the.
Some name.
Yes, a name, some sort of math.
But
I
also,
used to say it lots.
I think so.
we could just factor out x squared from each term.
Okay, so yes, so everything that's being said is good, and Noah's got like maybe a good first step would be to just factor this down a little better,
Yeah.
right? Pull out the x squared, the top and bottom, cancel that out. So I think that is a good, and then L'Hopital's rule.
But if we do that, we don't need to do L'Hopital.
Well, are you sure?
Yeah, because we have an angle.
Oh yeah, look at that. So L'Hopital, this is L'Hopitalable. Absolutely. Or factor, and you're right, Noah, it actually turns out to be pretty lovely. So we've got ax over x squared plus a squared. Yeah, that's a-okay. And then what is that limit? Hint, hint.
0.
So, work that all through. Now, what they ask you to do next is approach along a parabola. So now approach 0 along y equals, is it just x squared or the ax squared? Yeah. And so follow suit here. Just kind of mimic this argument and notice what I did when I replaced y. This will become just x squared here, and the answer will be very different.
Do you want us to do like the formal definition of a limit where it's
Like delta epsilon stuff or anything? No, God, no. No, please, 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 no, don't do
I
that.
find doing
No,
more.
I absolutely hate delta epsilons.
What?
Yeah, I did real analysis and those things traumatize me.
There's no trauma. No trauma. Only joy.
Math can't hurt you.
We survived.
When Labina says she like hated that thing, that means she like totally aced it, totally understood it, but yeah, I know something about you, my friend. Yes, you smack away over there. I know you. All right, so does this make sense? What needs to happen? Cool. Other things to talk about. Labina. Things you'd like to chat about on this assignment, my friend?
No.
Oh, okay, all right, I like that.
No, as in, not I don't have any questions. No, as in I didn't get time to look at them.
Oh, okay. So no.
Yeah.
Okay. Okay. That no started morphing along the way. Cool. Let's talk. If there's no other, yes.
Yeah,
Nathan, yes,
I have
sir.
a question. 218,
Yeah.
is it CFGHL?
Oh, what did I assign? Is that what you're asking?
Yeah, but then you also added, that's an EL. I'm just confused by that part.
No, that's an L. So like, I just wanted you to not think that was an I.
Oh, okay.
So I was like putting the phonetic spelling
Gotcha, okay.
of, yeah, thanks. I can see why that would be confusing as well. Real good? Seems like it. Okay. Cool, and I think we might just get some time to do some work in here today. If I can shut up and just start doing stuff. So I think I'll try that. See how that goes. Okay. So last time, let me ask you this: what is an analytic function? Let's just do a little review here and see what we remember.
Wasn't it like, something that's derivative at a point and then like all the points around it? So
Yes.
There's like a discounted that's all differential.
Absolutely. So it's a function from some subset of the complex plane into the complex plane, and it is differentiable at a point z0 and a neighborhood. I'm going to use this abbreviation. When I write MBD here, this means neighborhood. And I don't know if I've said that, but I've been thinking it and there's just not saying it. So this stands for neighborhood. It's a topology word, neighborhood. And what it really means is an open set around that point. So this is just an open set, really. It doesn't, usually we use a nice little disk, but it doesn't have to be. An open set about z0. So once you have differentiability here, and you also in some little region around there, it's all good no matter where you look. How do I discern if a function is analytic at a point?
So you divide it into two functions based on the imaginary part and real part.
Yep, so first step one, write that, yep. Then what?
And then you check if some partials are equal to other.
There's some
partials.
partial shit, yeah. What is that called? What are those two equations called? The
Cauchy-Riemann.
Cauchy-Riemann. So then we use the Cauchy-Riemann. Sometimes you hear people say Cauchy like Cauchy, like that. I've heard that weird, like kind of, I don't know, it sounds a little snooty to me. It's already French, right? It's hard to not get snooty. Okay, so now that I've insulted French people, let's see where I can go with this. The Cauchy-Riemann equations. What are those equations? partial of what with respect to x equals the partial of what with respect to y, partial of what, see if you can fill in the blank. Or look it up in your notes, or look it up in the book. Or just remember. Just trying to see how easy it is to find in the book. It's a free book. It's not my favorite book, but it's free. So we take that. What were these equations?
V with x is equal to the negative u.
Nice.
And the first one, I think uv.
That's what you're gonna say too, probably, I imagine. Yeah. Cool, so these are the equations. If the partials are continuous, and satisfied at a point, f is differentiable at that point. Cool, cool, cool. I wish I'd brought my other book, because then we could just work a bunch of problems out of it. So let's actually grab a problem out of here that we haven't assigned. Take a look at it. And you can help me out, because I don't have my list of what I assigned, what I didn't assign with me. So, I've got it marked here. Look at that. I did something. I know, it's amazing. So this function here, f of z equals 2x minus I times x plus y quantity squared. Let's just do this. This is actually problem K, 217K. Where is this differentiable? Is it holomorphic, aka analytic? And then find the derivative.
218, right? Like 17.
Probably. Yes, sir. No, I do mean 217.
No,
It's
not on my book. We must have different editions.
Yeah.
You see? Isn't that weird?
Yeah.
Huh. Well, I'll be damned. My printed copy says 217.
17.
Oh, no. Wait.
It's not
Oh, I see. Oh, that's so weird.
I just did the same thing to Hugo's computer. Where
I do it all the time. Yeah.
Not touchscreen.
I better get the new
Apple.
edition before I keep giving you stuff out of it. So 282, to whatever. Let's just do this one. So step one is to crank out those Cauchy-Riemann equations, see what they say, and figure out x and y values, where they would be true if they contain variables at the end.
This one? So that could do XY.
That's the u, right? Oh, 2x.
What's going on? What's wrong? Did I copy wrong?
Yeah.
Cause like, this one has
Let's
to
do
do
XY.
X and that do XY.
Oh, okay. Weird. Let me look. Maybe my copy, maybe I'm just like copying it wrong? That's a good question. I'm glad or you're not even asking, you're just like trying to figure out what the hell's going on. It is 2xy, sorry.
Okay.
Apologies, thank you.
Oh,
Sorry, I'm sorry.
it's doing fine before.
You were doing fine and I fucked it all up. I'm sorry, Noah.
You don't have to go that far.
I thought I'd be over dramatic so you could go, oh, it isn't that bad. Yeah, okay.
Oh, I guess I won't do that in the future. You know what, it is that bad.
It was like, I'm sorry, I'm such a fucking idiot. You're not a fucking idiot, really? That's great.
Oh, that reminds me of a question I have.
Oh, good. Very good. Well, let's make sure to get that after we work this through.
Okay.
Unless it's on this and you can somehow relate it to this.
Kind of, yeah.
Cool.
So, I think I did this problem wrong. But, okay, so when we're dividing, like, separating U and V, we're taking everything that's real for U and everything that's with the imaginary I with V. Right?
Correct.
Okay, so if it was like 2xy plus 5, U would be 2xy plus 5 and not just 2xy.
Correct. Yes. Yeah. That I is your like post for the V. Yes.
Okay. Because I was a bit confused, like if there was a constant added to 2xy would be, like, would we count the constant for
Cool.
2xy?
Yes. Yeah. So yeah, if that was 2xy plus 5 minus whatever, yep, then U would be 2xy plus 5.
Okay.
Yeah. It's definitely more interesting this way, I would think.
Yeah.
Yeah.
Oh, that's a minus.
Oh, you were saying that to yourself. I got it. Yeah. Okay.
My bad. Done something.
I would just like do sanity checks on our partials. So we haven't really done anything like this yet. You're gonna start getting equations out of this, and hopefully 2 equations and 2 unknowns. And then using those, you want those simultaneously satisfied. The Cauchy-Riemann equations have to both be satisfied at a point of differentiability. So you need to write out both the statements. Is this like where we are green, like headed down the same roads? Did you like, yeah.
If it's negative Vy, shouldn't it be 2x plus 4?
Thank you. Yes, I didn't put the double negative. Good call, would be like right here.
Yeah.
Yep, good call, man. Thank you. Oh, which actually makes life a lot better. That makes we have like this nice definite part. And then when you combine that with the other, so like this has to be for this to be. And so this combined with that, when we do those together, we get that x also has to be 0, because x is twice y essentially, negative twice y. So we have differentiable at z equals 0. That's the only point satisfied by the Cauchy-Riemann equations. So we're differentiable there. Am I analytic there? No. Why not? Grace, what were you gonna say?
Oh, no.
Okay, cool. Okay. Why not, Lou?
Cause like if it's only at 0 and it's not like an area around it, so that means that it can't be, cause that doesn't fit the definition.
Exactly, yeah, right, like you can't move away from 0 at all. You literally have this isolated point of differentiability. We want fuzzy regions of differentiability for analyticity. So this is not holomorphic or analytic anywhere. How do I find the derivative? And, oh, no, sorry.
That's what I was gonna ask.
Oh, okay, cool. So, think back to the derivative. The answer actually, did you know, Lou, were you gonna say?
Yeah, can't you just put like the derivative of u with respect to x and the derivative of v with respect to x together?
Yeah.
Or you can do that with the y, and I think you have to make it negative.
You are absolutely correct. So if you think about it was from the proof of the Cauchy-Riemann equations, or the derivation of them, that we can use a couple different formulas. So the first one is that we can just use ux plus ivx, and this means partial with respect to x here, sorry, I didn't mean to just introduce notation without identification. And then or, as Lou suggested, we can use the other ones, and that is the partial of u with respect to y minus I partial of v with respect to y. And this was where the equations came from, right? That if these were the same derivative, that had to equal that. That's one of the Cauchy-Riemann equations. And that had to equal minus that. That was the second Cauchy-Riemann equation. So we are just going to go through and say, all right, the derivative there. So at the only point of differentiability, z equals 0, the derivative is going to be d dz. I'll just go with that top one. Ux, which is 2y, plus ivx, which is that negative 2x plus y, I. But I'm at a point. I know what x and y are here. They don't get to roam around. So x is equal to 0 and y is equal to 0. And so the derivative there is just 0. Does that make sense? Really weird to just have this thing be differentiable at one point. It's kind of crazy. All right, any questions on this? Does this seem good? This should totally help you rock out that problem, I would think. All right, what do I want to talk about? I want to talk a little bit and then just give you some time to like work on that, and we can chat. So I just wanted to introduce this one particular term that you might have seen in other places. So definition, a function f in the complex plane where f is equal to u plus iv is harmonic. Have you seen that word before? I mean, you have.
In music.
In music, for sure, right? The harmonics on a guitar and things like that, which are always lovely bell sounds. This is in the study of like fluid dynamics and boundary value problems in physics, like heat distribution. We see this stuff a lot. So, is harmonic if it satisfies Laplace's equation. And what that means is that change this up a little bit. So sorry about this. just make f a real valued function. So f, which is a real valued function from the plane, the real plane, into the real numbers. Because we're going to talk about this for the u and v parts of our function. Yeah, sorry about that. I got that a little whack because I didn't make a note of it here in my notes. So, i.e., that the second partial of f with respect to x plus the second partial of f with respect to y is 0. And this thing here, this operation is called the Laplacian of f, and it's sometimes written with that del operator that you use for gradient in Calc 3, del squared f. Oh, at Calc 3 you probably saw this, right? Yeah, definitely. Probably.
Calc 3 was easier.
Calc 3 was what?
Years ago.
Yeah. Well, when you take all your math classes in the first year or whatever, everything's like.
Yeah.
Wait, how many years do you have left, Noah?
I have a semester after this left.
Oh, that's not much. Okay.
I'm almost done.
Lou's really bad off. Lou's got a lot of years ahead. We're gonna have to figure out some math for Lou.
You can do stats too eventually.
If
You
in
can
the
just
legend.
take a CS major.
Huh?
You can just take up a CS major. You're gonna be set for
No.
Don't do it. You'll
No.
go insane.
No, I was doing it, I dropped it, I was like, no.
Physics minor is easy.
Easy, that's great. I love that.
Psych minor, credits wise. Psych minor also
Oh,
credit wise easy, but you have to write a lot of papers. So I couldn't do it.
that doesn't sound good.
Papers are not fun.
We'll figure. We'll take
I
care
hear you.
Sophomore.
Okay. Cool.
And we'll be done with like almost all the math classes by the end of this year. So pretty crazy. All right, so
No, I'm short on credits then. I just have to take Gen X and just up it. Whatever I can fit.
There's a great brewing class you can take.
I was gonna say that.
Yeah, you can apply a brew certificate for like, what is it, 22 credits?
Is it 22 credits? I thought it was like 9 credits.
I'm taking 6 this semester, 6 next semester, and 10 next semester, 16 credits. So, yeah.
You like beer?
Huh?
You like beer?
No.
Well,
I
You
feel
could
like
learn
it's
to like
too
it.
young.
Especially on recording, so.
No, I don't like beer.
You can learn how to make it good.
No, I don't like beer.
look,
It's
if
not
you live
fun.
on
Pressure
campus, you
me.
can learn how to hide in the dorms.
You can learn how to what?
Nothing, it's fine, I don't have to make any beer for my final in the dorms.
I don't know. Don't try doing stuff in the dorms like
Look,
that.
I gotta do it somewhere.
Were we
I feel like we
talking?
should remember that we're on recording.
I'm
Yeah.
21 and it's legal to have beer in the dorms.
Absolutely.
Oh, okay.
That is true.
Did we talk about the student who grew shrooms in his dorm room that I knew?
No.
No. This poor guy. He's not gonna watch this, but he's not a Regis anymore. He got booted.
Oh,
Oh.
This guy, like, I met him in a math class. I liked the guy. He was a cool guy. He needed to work on focusing on school a lot, but I liked him. He, first off, he was like mining crypto in the dorms using their electricity and his computer,
Duh.
which is, that's smart, man, because the electricity is what makes it not profitable. So I was like, that's cool. It's a little criminal-ish, but, you know, good. And I just found out, yeah, he was growing mushrooms in his room. His roommate was like trying to go to med school, and they're like,
I heard
I
about
think
this.
I
Did you?
I feel like we've heard about
Was
this.
it last year?
yeah.
I think I heard about this from a different part.
That is West Hall?
I think so.
I'm kinda like totally detached from civilization.
You're that's smart.
During our CPA training,
thought it was
talking about
funny. I
it.
was like,
Yeah.
what?
Spill the beans.
Yeah,
I don't
he's,
know.
I mean, I don't know much beyond this unless you guys know more, but, I just know he was a knucklehead for doing that, so, anyway. So beer, it sounds like, no big deal.
Yeah, I can just pretend I'm making bread until I have to haul it back to
It will smell very similar. Yeah,
Yeah.
yeah, absolutely. That's some yeasty bread you've got there. Well, have a glass. You'll like it.
Yeah,
Drink a loaf.
call me in 2 weeks and it'll have finished rising.
All right, sorry. Back. What? What's going on?
Sorry, no, it's off topic.
Oh, okay. Oh, well, we can't have that.
No, never.
Cancelled.
Yeah, dude.
We have fire training too.
Yeah.
Oh, I
When
know.
is that?
Or
I have
tomorrow.
Huh? What time is it?
6:37, I think, or 6.
Guys, we're going on.
Our staff meeting
Sorry,
got
Dr.
canceled
T.
today, so I'm like.
It's okay.
that's cool.
It's all right. I do it. I take us off. I just, yeah, whatever. It's all good. We're all good. We're all friends. It's cool. Definition, or theorem, really, and I'm gonna kind of prove. If F is analytic in an open connected region, and F is written in that U plus IV form, then the real and imaginary parts of F are harmonic. So analytic functions are deeply tied to this idea of a harmonic function. They're parts. They're real and imaginary parts are harmonic. Let's just do a quick, easy proof, because this is a fun proof. Yay! Since F is analytic in D, notice I made D an open and connected region. That's actually, sometimes that's called a domain. A domain, and not like an abstract algebra, I don't even know if you guys got there, but a domain is an open connected set. So, we work with lots of domains.
Thank you.
Right? Did somebody just come in?
No,
Oh, okay.
that was great sneezing.
Oh, okay, got it. All right, well, the drugs are kicking in or something, I guess. Since F is analytic in D, the Cauchy-Riemann equations hold in D. So let's write those out, because it's good to practice writing. Take a minute, write the Cauchy-Riemann equations from scratch, don't learn.
We've got to stop using U and V for things as mathematicians.
Nah.
Why? That's interesting. What an interesting. I've
Because
never
they're
heard
so
anyone.
hard for me to tell apart my handwriting.
Oh.
Like I do a thing and then I have to go back and like redo the U's because they just look like V's.
You should write them like cursive. The U goes down and then the V goes up.
Or just make the V's really aggressively pointy.
It's true, yeah. And you don't have like little stems on your U's like that? Little like
No, I have bad
serifs or
handwriting.
Oh,
whatever?
like,
I just put,
yeah.
Yeah, I mean, if this is your U and this is your V, I mean,
That's what I'm saying.
how do you write U union V?
No, I named my sets differently. Oh, look, Killjoy was here.
Math jokes. It's great. A very small number of people get them, especially that one. All right, look, we got this. I want to show that this is the case. Can you help me? Please help me. You seem like people who know math. How can I move from that to this? Just, I don't know, can we try? What can you do?
You can like move those around and set it equal to 0. But I didn't see that.
We can, I think, let's not do that yet,
Okay.
but we can definitely do that, and we are gonna manipulate these, so you're definitely looking at the right place. Where are we at, where do we need to get, and what is the thing that gets us there?
Would you take the partials of both of those, like the ux equals vy, like do that of x, and then the uy vx of y, cause then you get the u double x, u double y, and then you've got vyx and vxy, and then those are the same, and then it's just a matter of them being opposites.
Solid, let's do that. So, differentiate, so first we'll show that. And to do that, I'm gonna take the partial with respect to x of each side. So this becomes u, second partial with respect to x, equals v. Y, first take this is the mixed partial, do the y derivative, then the x derivative. And then over here, we're gonna do we're gonna take the derivative with respect to y. So that becomes u y equals negative v xy. Now I have a question. This is looking a lot like that. I talked about this on Wednesday. When are these guaranteed to be the same? Because they're not always the same. What do we need, and whose theorem says that mixed partials are the same in different orders provided what? Because we don't have it in the hypothesis, we're just kind of like doing a loose proof, figuring out.
Provided that there's the weird thing that equals 0. Triple x, triple y, something?
Oh yeah, you're getting way too deep. No, it's actually, but it's like in a kind of more abstract level than like a con. I'll just tell you. Do you remember this theorem, Clairaut's theorem?
No.
Okay. Okay, Clairaut's theorem says that mixed partials are identical in any order if they are continuous. So if the mixed partials are continuous, you can do it in any order and you'll get the same result. So we're assuming here that this thing is continuous, this is continuous, this is continuous, and this is continuous. So Clairaut's theorem, I'll just kind of summarize it here, it says that mixed partials are independent of order if they are continuous. And so let's assume that, right? Otherwise there's no proof to give here. So we're going to assume that's true. Assume Clairaut's theorem holds. And it will, for the most part. If it's not holding somewhere, it's just like at a few points or a line or something, you can easily just remove that. Assume Clairaut's theorem holds. So take this and add equation 1 and equation 2. And add 1 and 2 together. So on the left side, I'll get uxx plus uyy equals vyx minus vxy. And these are the same by Clairaut's theorem. Mixed partials don't matter. So now we've got 0 on that side, and we see that u is a harmonic function. So I could even write this like this. That's a nice, beautiful summary. If you like, and I assume if you're a math person, you like notation. You like writing cool symbols, and that's just awesome. How could I now prove, I don't want to do it, but how can I now prove this?
I was gonna say you just do like a similar order of operations, but doing it like to get the v values that you want.
Yeah. So, wow, shit. To get this, so look now, if I take this equation and differentiate with respect to y, let's just kind of casually write that up here. I would get uxy equals vyy, partial with respect to y, and then do this partial with respect to what? Where am I going? X, right? So if I now do this with respect to x, I get uyx equals negative vxx. And then this, you can move that negative over here, add the two together, and you get the same thing. So let's just say similarly, and call that a proof. Now one last thing, boy, I'm not giving you much time to work. We can have a work day in here if you want. If that's something that we want as a class, like to have a day to just work on some stuff, we can do that. Just let me know if that's something you need. If Sydney was here, I know what she'd be saying.
Oh, definitely.
She'd be asking for a sleep day.
Oh no, she's gonna need a sleep day, I've got a feeling.
No,
Gotta
today
feel.
is her sleep day. She was like, I'm gonna eat and sleep.
Is that what she said? Cool. Good for her. Good for you, Sydney. Good for you, friend. I know she's actually gonna watch this too, because she's that kind of person. So what if, this is kind of a weird question, f equals u plus iv, and u, we know u is equal to x cubed minus 3xy squared minus 5y. How can what could v be to make this a harmonic function? So we can start off with something, we only have a portion of the knowledge, maybe just the real part or the imaginary part. How do we build a function that is analytic from this? So use this to construct an analytic function. And the way to do this is to produce the harmonic conjugate of u, i.e., find the harmonic conjugate of u and make that the v in f equals u plus iv. Let me just check through my notes, make sure I'm not going crazy. Yeah, you're gonna like this. This is even easier. We don't have to go to second partials. If you were in Diffie-Q with me, this is gonna look very familiar. If you took Diffie-Q and you studied exact equations, this is that process. So you've done this. This is nothing more than exactness in that Diffie-Q sense. And it's really cool how these processes just kind of span across mathematics and show up in different ways. So, step one. I'm just gonna write u equals, just write out what I got. U equals x cubed minus 3xy squared minus 5y. This all is going to come down to the Cauchy-Riemann equations. I'm going to find u with respect to x. And so here that's 3x squared minus 3y squared. For f to be analytic, we need v with respect to y equals u with respect to x. That's from one of the Cauchy-Riemann equations. So that's going to help me link to v. I can move from the partial of u with respect to x into the partial of v with respect to y. So we know, thus, let's thus this thing, vy must, and I'm going to put a must here, equal 3x squared minus 3y squared. Cauchy-Riemann's Holden. How do I get to V? So from here, this is step 4, what up to V? What's that? It's cool. Yeah, it's starting to get serious now.
Vy to V.
Yeah, how do I move from the partial of V with respect to Y to V? What mathematical operation?
Introduction.
Thank you. You win. Alright, so integrate.
Very funny.
Integrate with respect to Y up to V. So V equals, what is the antiderivative here?
X. What are we doing? Y.
With respect to Y.
3x squared y
Beautiful.
minus y. I think plus c.
3
Y.
y cubed, I think.
There we go.
What was
Above
y cubed? Oh yeah, sorry.
yeah.
Y cubed.
power rule, right?
Yeah,
So
yeah.
it goes up to Y cubed, divide by the 3, so we got Y cubed plus, but I love that, a constant that could depend on X.
Yeah.
Because if I differentiate this with respect to Y, that would disappear, and I would still have that, so I want the most general constant of integration. Do you remember this from exact equations? If you had that, yeah.
It's pretty exact memories.
Well, fair enough, I brutalized you all with,
Oh, you did take V, right?
what's that?
Yeah. He's asking about the exact thing.
Oh. So how do I find, so step 5 is now find C of X. How do I do that? What do I do? What other piece of information haven't I used from complex analysis in the last week that I used first? I used it already, but I haven't used all of it.
The rest of it,
The Cauchy-Riemann. So let's write that up here. That is the U with respect to Y equals negative V with respect to X.
So negative, so V with respect to X has to equal negative, or has to equal 6 XY plus 5.
Yeah, so let's just do a little scratch over here. So we need this to also be satisfied. And this is what we're going to do in this part. We're going to find C of X so that Cauchy-Riemann is satisfied fully. So we need U with respect to Y equals negative V with respect to X. I've got V, so it's nice to write it out this way. So V with respect to X must equal U with respect to Y. That's cool because I got Y right, U right here. And so that's going to be negative 6xy minus 5. Does that make sense? Check me out, make sure I'm right. I took the partial of this with respect to Y, and then I forgot to negate it, didn't I? So I need one more negative on there. Because I have this negative, and then the partial of U with respect to Y is negative 6xy minus 5. So in other words, we're going to need V with respect to X to equal 6xy plus 5. So let's check it out. I'm going to take the derivative of this now with respect to, so let's actually write that out. Partial of V with respect to X is 3x squared y minus y cubed plus c of x. This goes to 6xy, looking good. Dead, because I'm differentiating with respect to x, the y cubed, poof, plus c prime of x. This is this is Vx. Let's actually write that. And that must equal this. This thing over here, this must equal 6xy plus 5. And it becomes apparent now what C prime has to be. Is another thus in order? Absolutely. Thus, C prime of x is that 5. And I want to find C, so I have to integrate. So I'm taking antiderivative. With respect to x, I get 5x. I could tack on a constant if I want, that's okay. So this is now an arbitrary constant. What we're saying here is it doesn't matter what that is. Arbitrary real constant.
Yeah, it can't be arbitrary?
No, because we are assuming that u and v are real valued, and we tack that y on to get the imaginariness. Does that make sense?
Yeah.
Yeah. If things start getting weird if we start twisting them up like that. I mean, I guess it could, Noah, and it'll work out fine, but let's not.
Okay.
Let's just say, just for clarity, leave it there. And so I can summarize. In summary, v is equal to 3x squared y minus y cubed plus 5x plus some constant. And so then I could just summarize my final answer and write out what f has to look like. And I will. Just for the sake of completion, I will say that this f has to look like this. So f is x cubed minus 3xy squared minus 5y plus I times the beast we just built, 3x squared y minus y cubed plus 5x plus c. So yeah, no, I guess what I was thinking is that this could be imaginary, and then it, I think you could make it work no matter what. It's a good question. That's all I have for you today, my friends. I don't even think you have homework like this. Not yet, anyway. Do you want to call it a day? Do you want to hang out here and work on stuff? What would you all like to do? Noah's probably likes to go get ready for stuff.
Take a nap. Honestly.
Okay, we can call it early today. That's not a problem, is it? Who's coming to math club on Wednesday? Cool. Now who's really coming to math club? Everybody? Okay, you're really coming? All right,
I
all
was
right.
there last time.
Oh, that's right. Everybody's coming. Nathan, you gonna be able to make it?
I just,
Awesome.
the first 30 minutes. Cause I have class.
Oh, right. That's great. We're gonna try to do it every 2 weeks, so.
Might this class this week, cause we're gonna have a birthday party on the math club. I don't know, Oasis is not here. He's probably gonna talk to you about that, but yeah.
Yeah, a little birthday party, right? Math birthday
And then
party. I
some-
love that.
some math club.
I have to. Maybe I can get Marie to get us some cake.
Ooh, yeah.
Right? You like
I
cake?
like donuts.
You like donuts?
I like anything that has chocolate in it, even though I hate sweet stuff. Like I
Chocolate can be not sweet though. That's what's
I
nice
hate
about
bitter
it.
chocolate though.
Let me shut this recording down.